Today we are going to start by adding postulates and theorems to the same postulate list you started with lesson 3.2. First, copy the diagram for this one. The converse of the same side interior angles postulate says, if two lines and a transversal form same side interior angles that are supplementary, then the two lines have to be parallel. In other words, they're saying if you have same side interior angles like this 140 and 40 degree same side interior angles that add up to 180, 40 plus 140 equals 180, they are supplementary, and if they're supplementary, that means the lines they are between are parallel. These two vertical lines next to each other is mathematical shorthand for the word parallel, so out loud you read this as line A is parallel to line B. Now, I want you to compare this first postulate on page 2 with the first postulate on page 1 that you already filled in. Scroll up and look at that first postulate from 3.2. See how similar the same side interior angles postulate is with the converse of the same side interior angles postulate? The diagrams are nearly the same, the names are nearly the same. The only difference is that they are backwards versions of each other. Remember the word converse in chapter 2? You learned that means that it's the backwards order. You're switching the order of the hypothesis part of the sentence after the if with the conclusion part of the sentence after the then. If you look at the conditional sentences that make up these two postulates, they're just swapped backward versions of each other. The main idea is the original same side interior angles postulate starts off with you knowing that your lines are already parallel, and you use that to figure out an angle. The converse, you start off by knowing both your angles, and you use that to figure out that the lines are parallel. Here's the next box down, converse of the alternate interior angles theorem. If two lines and a transversal form alternate interior angles that are congruent, then the two lines have to be parallel. If you know both angles, they're congruent to each other in the alternate interior angle pair set, you can conclude that line A is parallel to line B. You're going to notice that all four of the converse theorems you're filling in today are used to prove that two lines are parallel because you know something about the angle pairs. So it's really just a backwards version, a converse version of the four theorems you filled in last class. Here's the third one, converse of the corresponding angles theorem. If you notice that your corresponding angles pairs match, they're congruent to each other, that tells you that the two lines that they're attached to have to be parallel. A is parallel to B. Last one for today, the fourth box, the last one on page 2, converse of the alternate exterior angles theorem. If your alternate exterior angles pair are two congruent angles like 140 and 140 degrees, that tells you that the lines they're attached to here, that the transversal is crossing, those two lines have to be parallel to each other. So to sum it all up, your original four theorems from last class, you use those to solve for missing angles. The converse versions for today's class, you use to prove lines parallel to each other. Now go to your 3.3 notes worksheet. I'm going to pull up a question on my screen that's not on your worksheet to just kind of get your brain using these theorems. Take a look at this diagram on the screen. Would you say these two lines are parallel or not? If you said no, they're not parallel, very good, because if you look at this angle pair, they're corresponding angles, but they do not match. They are not congruent. One's 30, one's 32. Because they're not equal, then one of these lines must have a slant or slope that's very slightly different from the other line. At first glance, they look like they're parallel, but because these angles don't match, we know that if we continue the lines far enough, they would eventually run into each other. It's just the slope is so similar, it's hard to tell that they're not quite matching. Try question 1. If you said yes, they're parallel, and your reason was converse of alternate interior angles theorem, well done. Remember, the converse versions are what you use to prove lines parallel. And these are alternate interior angles, opposite or alternate sides of the transversal, and interior, the two lines. Try question 2. This one's a bit trickier. If you said parallel because of the converse of same side interior angles postulate, well done. If you look at these angles, at first a lot of people want to say not parallel because they don't match. But look at what sort of angle pair they are. They're same side interior angles. They're the only pair that aren't supposed to match. They just need to add up to 180 instead. They do add up to 180, so you could say yes, your lines are parallel because of that converse. Now, occasionally on the homework, you're going to still solve for angles, but you'll notice they'll phrase the initial question a little bit differently than they did with lesson 3.2. The questions will, in 3.2, originally would say things like, your lines are parallel and you know it. Solve for the missing angles or the variables in the angles. But today, with lesson 3.3, they're going to say what value of x or what value of y would make the lines turn out to be parallel. But the way you solve the problems are the same as what you did last lesson. You just say, well, to make these lines parallel, alternate exterior angles would have to be the same size. And then you solve for x. You can subtract 2x from both sides. If you show your work, well done. I did not do so myself this time. After you subtract 2x from both sides, then you can add 63 to both sides, and you get x equals 65. Try question 4. I want you to notice that these angles are definitely not equal. You have a little narrow acute angle and a super wide obtuse angle. But they're not supposed to be equal because they're same side interior angles. And same side interior angles just need to add up to equal 180 degrees. Then you could add your like terms. Because you're not writing a proof, you're just solving, you're allowed to do some steps in your head, like adding the 33 and 7 without actually writing them next to each other. You can subtract 40 from both sides and divide by 14 to get your final answer. Next, you're going to write down 3 very important definitions. So at this point, you have a lot of familiarity with the 2-column proof. This is the most common type of proof in geometry, and it's the one you spent most of chapter 2 practicing. You have a T-chart with 2 columns, statements on the left and reasons on the right. So that's your most common proof, the one you already are very familiar with. A second type of proof is called a paragraph proof. This is writing the same steps and reasons out that you would have in a 2-column proof, but you're writing it with complete sentences instead. You had a fill-in-the-blank paragraph proof on your 2.6 practice worksheet. So you've actually done at least one of these already. There's a third type of proof, and today's the first day you're going to write one of these. The third type of proof is called a flow proof. A flow proof is a lot like a flow chart, except with the steps of your proof. You have arrows to show the logical connections between different statements in your proof. You still have the same series of statements and reasons, but it's organized in a way where visually it's very easy to follow how all the steps relate to each other and build off of each other. Question 5, write a flow proof. We're going to walk through this one together. So your first step would go in the first box, and that would be the given. Angle 2 and angle 3 are supplementary. You could write it like that, and then the reason can just go right under the box. If you could fit it inside the box, even better, but I couldn't quite manage to do that. So what we know at this point is that 2 and 3 are supplementary. They would add up to 180 degrees. It is also a good idea to look ahead at your end goal. Your end goal is to prove that these two lines are parallel. So knowing that our goal is to prove two lines parallel tells us that somewhere near the end, we're probably going to need to use one of the 4 converse theorems from the beginning of notes today, because those are our 4 options for proving lines parallel. So you can keep that in the back of your mind. Now there's something interesting about how this flow proof is set up. Notice how both of these steps lead to the third step, and how this step has nothing that's pointing to it. This step does not have an arrow from the given step. In other words, this step must be something you were able to figure out without looking at the given. So it must be something you know to be true just from looking at the diagram. So looking at the 3 labeled angles, is there an equation you can make or a fact you can figure out about 2 of those 3 angles just from looking at the picture? Look at angles 1 and 2. What can you figure out about 1 and 2? Just from looking at the picture, you can tell that angles 1 and 2 have to be supplementary because they make a straight line together. They have to add up to 180. They have to be supplementary if they make a straight line. So that's something you could figure out from the picture. It's not building off of the given, so it's kind of a separate introductory step. Your official reason for that is called the linear pair postulate. The linear pair postulate was actually one of the postulates you took notes on back in chapter 1. Yes, in chapter 1. Remember, linear refers to lines. So the linear pair postulate says if you have 2 angles or a pair of angles that add up to make a straight line, they have to be supplementary. Now somehow step 3 is building off of both of these steps. So let's compare these 2 steps that lead to step 3. Angle 2 and 3 are supplementary. Angle 2 and 1 are supplementary. Oh, that's interesting. There's a repeat. Angle 2 is mentioned in both of them. Now, if both angle 3 and angle 1 add up to angle 2 to equal 180 degrees, then angle 3 and angle 1 have to be congruent to each other. That's the only way that they can add with the same size angle, angle 2, and still equal the same answer of 180. If you look at your chapter 2 postulate paper notes, this is actually using the congruent supplements theorem. The idea that 1 and 3 have to be congruent because they're supplementary with angle 2, the same angle. Now you can see there's only one more step in the flow proof. You already kind of know what the last step has to be, though. It has to match the proof. So you know the last bubble will just be whatever's in the proof. C is parallel to D. But now we need the reason for that. Well, you're able to prove that C is parallel to D because of this third step, angle 1 congruent to angle 3. What sort of angle pair are angle 1 and angle 3? If you said alternate exterior angles for angle 1 and angle 3, well done. So to prove the line parallels, it would be converse of alternate exterior angles theorem. The last thing we need to talk about today is how to write a proof for a theorem or postulate. So for question 6, we're actually going to write the official proof for a postulate. This is actually how mathematicians get famous, is if they write a proof for a theorem or postulate. They prove why it's true, and then they become big name mathematicians. All right, first note to make on your paper is in that blank under to prove a theorem or postulate. To prove a theorem or postulate, you need to first identify what the given and the proof are, and to do that, it takes a little bit more work than normal proofs because you have to kind of dissect the conditional sentence of the postulate to figure out the given and the proof. Here's the rule. Write this down. You can figure out the given part of your proof by looking at the hypothesis, the if part of your sentence. And the conclusion half of the sentence, the then part, that tells you what you're trying to prove. So first half of the sentence is a given, second half is the proof. So jot down that note, and then we're going to use that to figure out what the given and proof is for this theorem. If a transversal intersects two parallel lines, then same side interior angles are supplementary. So the if part is a transversal intersects two parallel lines. That's kind of long for the given, and it's also not very specific. So we're going to make that a little bit more specific so it applies to the diagram we're using to write this proof. So instead of just writing a transversal intersects two parallel lines, we're going to name what parallel lines we're talking about. We're talking about L and M being our two parallel lines. So the shortest way to write the given is to just say L is parallel to M. We're translating that hypothesis, that if part, so that it's talking about the two parallel lines specific in our equation, or in our diagram. The proof is the conclusion in the sentence. Same side interior angles are supplementary. So let's make that specific for our diagram. Which two angles in the picture are our same side interior angles? Angles 2 and 3 are same side interior angles. So you would say, instead of the same side interior angles are supplementary, you would say angles 3 and angle 2 are supplementary to make it more specific for our diagram. Go ahead and fill in your first box. L is parallel to M, given. Now, one of the rules about writing theorems for postulates writing proofs for theorems and postulates is that when you're proving a theorem or postulate, you cannot use that theorem or postulate itself to write the proof. So we can use any of our previously learned theorems or postulates except for the actual same side interior angles postulate, because that's what we're trying to prove. We can't circular logic it and use it in its own proof. So that means we could use other type of angle pairs. We could use alternate interior, alternate exterior, and corresponding angle pairs. So let's think about other angle pairs we have labeled in the diagram that we can say something about. We have angles 1 and 3. What sort of angle pair are those? You could say angles 1 and angle 3 are congruent because they're corresponding angles. Remember, if we're writing an equation about angles, then it's the original angle pair theorems, not the converse version. So just normal corresponding angles theorem, not converse. Now this third box, notice how it's not building off of the given. There's no arrow from the given. So it must be something we could figure out just from the diagram with our labeled angles. We can say something about angles 1 and 2. What can you say about angles 1 and 2? Angle 1 and angle 2 have to be supplementary because they make a straight line. In other words, because of the linear pair postulate. Now, you know what the end goal is. You know that the last box is going to be what we're trying to prove. Angle 3 and angle 2 are supplementary. We just need to figure out why we know that. Well, notice how similar this final sentence is to the one you had in step 3. The only difference is step 3 had angle 1 where we have angle 3. Oh, you know what we did? We just used step 2, that angle 1 and angle 3 are congruent, and we replaced angle 1 in step 3 with angle 3. We just plugged in angle 3 where angle 1 used to be since they're equivalent angles. If you're plugging something in, what property is that? Substitution property.